Here are two warnings about L'Hopital's rule. You have to make sure that this is truly the case. And I could probably add in that G prime A does not equal 0, right? That it's not 0. If this is not true, if you don't check these conditions, then applying L'Hopital's rule will just be nonsensical. You'll get a nonsense result. Second, looking at the formula, it's tempting to think that you're supposed to use the quotient rule. Right? It has f prime x over g prime x. But of course, that's not the quotient rule. Right? That's the derivative of one function divided by the derivative of another. The quotient rule was actually much more complicated than that. And we'll review the quotient rule a little bit later. For now, I would like you to try this practice problem. So try to apply L'Hopital's rule to this question. And so press pause, give it a try, and then continue with the video and we'll solve it together. All right, I'm going to start with the numerator, and I'll denote it as f prime x. That's the derivative of the numerator, and I get 1 over x, right, log x. The derivative of log x is 1 over x minus 1. What about g prime of x, the denominator? Well, I've got to apply the chain rule, but the interior, the derivative of the interior is just equal to 1. Now I'm going to take 1 over x minus 1, divide this whole thing by 2x minus 2. Now maybe I'll try and evaluate this at x equal 1. I get 1 over 1 minus 1. 2, 1 minus 2 equals 0 over 0. Wait a second. What happened to L'Hopital's rule? Why didn't this work? Well, it was kind of a trick question. I forgot when I asked it. It was a bit of a trick question. So by taking the first derivative, it didn't work. But notice that we still have the conditions to take the derivative and apply L'Hopital's rule again. Notice that although it's still 0 is equal to 0, we have f of x is equal to g prime of x is equal to 0, and g double prime of x is equal to 2. So let's try it again. Let's take the second derivative of f of x. We're going to have, well, I know that this thing here, that's like x to the negative 1 minus 1. The minus 1 is just gone. So, but we're going to have this negative 1 coming down. So there's my derivative for that part. Then g double prime x, well, we already showed that that's going to be equal to 2, so I don't have to do that. Now, bring them together. We've got negative x to the negative 2 over 2. Right, this is my f double prime x over g double prime x. And now I want to evaluate this at x equals 1. Now, maybe before I do that exactly, I'm going to have 2x squared like that. Negative 1 over 2, 1 squared. And we're left with negative 1/2. So if we want to find the limit of this kind of ugly expression. We ended up having to use L'Hopital's rule twice. But when we did, it worked out pretty nicely. And it wasn't too onerous a calculation to do so. All right, here are all the rules. We're going to walk through them together. So what is the derivative rule for a constant? Well, f prime of x here is just going to be equal to 0. Constants disappear. Multiplicatives, so if I have 4x, for example, and I'm going to use the power rule down here, g prime of x is equal to 4. The multiplicatives, they remain. Multiplicatives always remain. What's the power rule that I just used up there? What's the formula? Well, if I've got a to the x, oh, I guess I don't want to do that, do I? Let me try that again. Let's suppose I've got f to the x is equal to x a, like so. Then f prime of x is going to be equal to a x a minus 1. And so the derivative of this thing is going to be equal to 8x. What is the derivative rule for the product of two functions? Well, that's the product rule. And if I have f of x is equal to fx times gx, then the derivative of capital F is going to be equal to the derivative of the first times the second plus the first function times the second one. What is the derivative rule for the quotient of two functions? Well, if I've got f of x, big F of x, is equal to f of x over g of x, then f prime of x is going to be equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared, like so. What about composite functions? That was our wonderful chain rule. In fact, we couldn't even answer those previous examples if we didn't have the chain rule. And the chain rule says that if I've got something like f of x, big F of x, is equal to little f of g of x, then the derivative of big F of x is going to be equal to f prime g of x times g prime of x. Right? And in Leibniz notation, it was d of f over d of x is equal to d of f over d of u. Or I guess in this case we're not using u, we're using g, times d of g over d of x. The derivative of the outside function multiplied by the derivative of the, well, inside, I guess I'll say inside. Exterior, interior, sounds a little bit more formal. The exterior and the kernel being the inside, is even better. What is the derivative rule for the natural exponential function? That's the craziest rule of them all, right? It's itself. It's itself. And so we have, almost by design, because then we have the relative change is always equal to 1. The relative change is always equal to 1. It's constant. What is the derivative rule for exponential functions that are not the natural function? Or I should say the natural exponential. Well, it's going to be kind of similar. It's going to be itself. Oops. It's going to be itself multiplied by the log of the base. So if we've got big F of x is equal to ax, then big F prime x, the derivative of big F, is going to be equal to ax log a multiplied by log a. What is the derivative rule for log functions? Well, it's a pretty easy one. If we've got log x like that, we've got a multiplicative. The multiplicative always stays where it is. And log x just becomes 1 over x. So we could have 4 over x. What is log differentiation? Oh, that's a tough one, right? Remember, we have something like, well, I won't use y. I'm going to do it like this. F of x is equal to something like that. That was the example that we used. And if we took the log of f of x, we got x log x. And then we could actually show that the derivative of this thing was, I have to use the chain rule on the left-hand side. We have, I'll do log x plus x over x, 1. And then we had f prime of x is going to be equal to, I'll do it fast because you can always go back and see all the steps later. Or sorry, all the steps we did earlier. Finally, we've got L'Hopital's rule. And if we look at this one, x is going to a, so we get a squared minus a squared over x minus a. Well, if I want to take the derivative of the denominator, I'm going to get 2x over 1. And then now I take the, let x be equal to a, and I get 2a. 1, or just 2a. Hi everybody, Robert J. McEwen here. I just want to congratulate you on making it through all these videos. There sure were a lot of them. You learned a lot of rules. There was a lot of mechanics involved. You now have the foundations for a very good toolkit to help you through your undergraduate career in economics and beyond. And hopefully, at this point in the course, you're feeling more comfortable and more confident in yourself with your quantitative abilities or your numeracy, which is a very highly desirable skill set, and you will be rewarded for it financially in the workforce one day, I promise you. Again, congratulations. I wanted to sort of appear at the end of these videos because I feel that you must have done a lot of work to get this far. So congratulations. I hope to see you soon. And if you want to give me any feedback on these videos or what you think about the course, I'm always happy to hear from you. Bye-bye for now.